Okay, so I'm just gonna briefly review what we talked about this week. Yeah. So we have seen a bunch of some application of these two queue subroutine, which is one is local min cut and one is isolating cut. So okay, so there are for local min cut we have seen an application of computing global min cut in directed graph, right? Directed graph in this time. Okay. And here is when I mean min cut, I mean edge min cut. Right. However, it's gonna be not too hard to extend the whole algorithm for both local and global to find vertex min cut. Yeah. So what do I mean by that? I mean, if you look at the problem where you have a graph and you ask, can you delete k vertices from the graph so that the graph become disconnected, right? Then one can define, okay, let me PowerPoint. One second. PowerPoint. Sure. Okay. Yeah. So what we have seen in class is this problem. How to solve this problem where you ask if there is a cut such that the number of directed edges going out from a cut is small, right? And also you want that the volume of this set L should be small too. You want to detect such a cut, right? So that's the problem. Now we can ask kind of similar problem, but for vertex setting. That is, you ask if there is a set L containing seed X such that the neighbor, like the neighbor set of L, the node that is incident to L, that is adjacent to L, is smaller than K. So now it's like about vertex cut, right? And you can still, and the same thing here now, that the volume of L should be small. And otherwise it should return, like if you either say that there is no such cut, or you say that you return a cut such that such cut L such that the neighbor set is small. Like after removing this K node, the neighbor of L here, L is disconnect and the volume of L is something like nu K. Well, this is gonna be possible too, and can you tell me, like, there is actually a reduction which is quite easy, like how to, like, if you can solve this one in the directed version, you should be able to solve this one too. Can you suggest how should we solve this vertex version using this one? Any suggestion? So, yeah, the idea is actually going to be quite simple. That is, suppose that you have a graph so you have the graph like this where you want to find, let's say that this is a graph where you want to find vertex cut, and now if there is an edge between two nodes like this, then what you do is that you split each node V into two nodes, V in, V out, right? And now you add an edge directed from V in to V out. Yeah. And now also the same for every node, you split it like this. Yeah. Okay. And then if there is an edge between U to V, you just add an edge from U out to V in and V out to U in. So just do this for every node, maybe except the seed. The seed X, you don't split it, but every other node you split a node into in and out node. So in picture, it's gonna look like this. Like suppose that there is if this is a set L, right? And if there is a vertex cut of size 2 that separate L from the rest, then what will happen after that transformation is that once you split the node, then you're gonna you see that this out edge gonna correspond to this edge that go out from set, just correspond to the node here. Yeah. So basically, the fact that you split the node and have an edge from in to out, if you delete that edge between in and out, that is like deleting a node basically. So with this transformation, then you just transform the graph using this splitting and find out cut, like a directed cut with small number of out edge in the new graph, and you can the solution in this directed graph correspond to a vertex cut in original graph. Yeah. Does it make sense? Yeah.
What if U this cuts the U out and V H?
So yeah, that's a good question. So, well, if you ask like, what if it cut this kind of,
No, the other. It is in the opposite direction.
which one
The
then?
one neighboring to that.
The one what?
The right side of that.
You mean this one? This edge?
No, the U out to V in H. In the previous slide, the U out to V in H.
Right. So, okay. So, maybe
I think it's because every vertex of the vertex must have that head go inside.
yeah. So, suppose that your solution doesn't cut this split edge. That's what will happen, right? And basically, if your solution, let's say that this is some u in and u out, and okay, there can be a lot of edges here, and a lot of edges here. Okay. Suppose somehow that your solution is such that it doesn't cut through here, but it somehow chooses to cut it in such a way that maybe here or maybe like this. Then it's gonna be always better to just like if you look at this cut, change the cut a bit, then it's gonna be always better. Yeah. Or not worse, like if you have only degree 1 in that go in here, okay, maybe this cut is a valid min cut, but you can always like change it to this cut and doesn't change the cut size. Yeah.
Without loss of generality, we can assume that it's cutting this edge. Right?
Yeah, right, exactly.
Because the only edge going out of V in is that V out edge, not exactly.
Yeah,
Yeah, we can always change it.
right,
Probably easier to argue. Given a vertex cut, you can find an edge cut. Given an edge cut.
right. Yeah. You can find a given a vertex cut, you can find this cut that cut through this for sure. But given a cut in edge setting, you can make some change that doesn't increase the cut size and make it correspond to a vertex cut. Yeah, so now, so once, once you know that, okay, you can actually solve this local min cut even in the vertex setting, then you can use it again to solve. Then you can use it to solve a global vertex min cut in where k is opt or okay, maybe I should say that maybe instead of this, like checking k vertex connectivity in this time, and the strategy is going to be very similar to what we did for the directed edge min cut, right? So there will be two cases. The case when the cut is balanced, like if the cut is very balanced, so Somehow the computer is super slow. Yeah, just like in class really. Like if you have a vertex cut such that two sides are balanced like this, then if you sample k pairs of edges or k pair of nodes proportion to its degree, then you're gonna get two nodes on the different side, and you use Ford-Fulkerson again, right? So like you sample k pair of nodes. You sample k pairs of nodes. One of the pairs is going to be on the different side, and each of the pair you spend mk time using Ford-Fulkerson. Otherwise, it's unbalanced, and if the volume of on the small side is like something like 2 to the I, then if you sample m over 2 to the I edges or m over 2 to the I node proportion to its degree, with probably proportion to its degree, one of them gonna be inside L again, right? And you call this local vertex min cut algorithm. So sorry, somehow it's super slow. Okay. Yeah. Then you call for each of the sample you call the local vertex min cut, and the running time is going to be, for each of the call, it's going to be this much. And this is how the running time is mk squared. So really the same idea as in class, right? Okay. Right, so this is the, one second. So this is the algorithm basically, and maybe it's worth it to mention, like, although this algorithm is very simple, I want to tell you about the history a bit. So like basically the problem of checking vertex min cut, like whether the graph is k connected or not, people have tried to solve it, and for small k, like k equals 3, it has been solved from the 70s already. And people have conjectured that it should be able to solve, we can check it for any k in linear time. However, no one have solved it, and for k equals 4, like people got stuck at n squared already. It's not near linear. But for H connectivity, it is basically solved a long time ago. But in the vertex setting, but this is for H connectivity in undirected graph that people solve, not the directed case. But anyway, in the vertex setting, even in undirected graph, like no fast algorithm is known. Like for general K, the algorithm that people have shown is kind of much slower, like takes a lot of MACflow call, and there are many other ideas that people have tried, but still the best running time is something like MN. That's the best running time. So there are some other algorithm like this, which is slower than MN, but deterministic. But the point is that, let's say the graph is sparse, then nothing is really like, it has been slow, like slower than n squared. Like all of this bound, when the graph is sparse, it just simplifies to this kind of thing, which is n squared at least. Yeah. So this is, and this n squared is like actually known for like 50 years. But yeah, the algorithm I show you it takes time like mk square, and when the graph is sparse, we know that k is going to be constant too, and this is now linear. So this very simple technique can like make progress on something that people got stuck for 50 years. Right. So just want you to appreciate it. Okay. All right. Okay, and
So is this technique not known before?
so basically there are some techniques which takes something like so once I discovered this algorithm, I tried to look back in the literature, and so the algorithm that I taught takes this much time, right? And there are some algorithms in the literature that take this much time, and which is not good enough, right? Because in order to get like your running time, the running time that we need is something like we call the local algorithm this many times, and each of the time we spend new k squared. So at least the dependency on new should be linear, right? So this one is actually like known long before in this in the literature of property testing, and basically once you get this one, then you improve a lot of things in property testing literature too. But yeah, you're right. Like the problem of trying to solve something locally is just supernatural, and like so people have looked at it, and the kind of people that look at it is property testing people, and there they don't care much about dependency on new or k. So as long as it is like local, then they're fine. That's why they can stop here. Turns out that it is useful for just classical problem like vertex connectivity too. Yeah.
Were you able to make it deterministic also?
Oh yeah, and so actually let me tell you a bit more about what is known about this local thing. So this is known like in 90 something, and this is by I think Go Reich. Okay. And then actually, so what and this is deterministic. Yeah. What we have here is randomized. This is with Danupon, me, and Sarachai, Yingjaran, Tawanchai. But actually, before we get this thing, we get something like this times this. And this is deterministic. And you see that once we get something like this, then if you use it here, you're gonna break n square already. You're gonna get some improvement, which is it's gonna be faster than n square, but not linear yet. So this is how we get this thing first. Like we break n square bound, but it's not near linear. But this is deterministic. By the way, I should really mention that it turns out that there is one algorithm that actually before our algorithm. So I forget the author. But the running time is actually this thing, and this is deterministic too. But what is nice about this is that if you actually use this algorithm in our setting for vertex connectivity or edge connectivity, at the end here even if this is k, like not k squared and this is k to the k, you're still gonna get like something like m k to the k, right? And this is now still linear when k is constant. Yeah, but it's just a bit worse dependency on k. So actually using this algorithm that is known before ours, it's gonna give linear time algorithm for vertex connectivity for constant k already. It's just that this connection is not seen. Yeah, was not seen. Right. Oh, you're right. Yeah. So very good. So even if you have deterministic local algorithm, using this framework is going to be randomized. And right now, very good. So the best deterministic algorithm for vertex k vertex connectivity, deterministic k vertex con. It is something barely below. It's something like this thing, yeah. So it's not near linear yet, but it can be like the n square bound can be broken already. Yeah. But I believe that one can do it in linear time. Yeah. At least for constant k, that should be possible. And this is one of the paper that I was co-author, and we use expander techniques to get this kind of bound. Yeah. Okay. All right. Okay. So for the cut matching game, so we have seen like we have seen the game. We have seen like one deterministic algorithm which is slow, and I have just briefly talked about the randomized and fast algorithm. Right. So actually, is there any question about the cut matching game so far? Okay. Otherwise, then I'm gonna tell you a bit more about how to like the deterministic algorithm that we described in class. It takes exponential time because we need to solve NP-hard problem. But yeah, if we have some subroutine that is kind of approximate, then we can use this approximate subroutine to solve it too. So now I'm gonna describe precisely what is this approximate subroutine that is enough for us. Okay. And we can, let's say that I have this subroutine. So let's say that I'm given a graph. Okay, input, graph, and output, either return a balanced path cut, which is what we want for almost all the rounds, right? Cut S where psi of S is. So this is exactly the same thing as the kind of cut we get in the algorithm. However, if we can just say that if we cannot find this kind of cut, then what if we say we just need to return some cut S, maybe call it AB, such that is an expander. So in class we argue that okay, like we get some cuts where the side, the B side is already done, is an expander, but this kind of subroutine is gonna be too hard because actually just checking if like approximating this like suppose that we have this subroutine, we can use it to approximate the expansion of a graph up to constant, right? At least like if we say that let's like if the graph have conductance, because this is still NP hard. Why? Because suppose that if you return, if the graph is such that, so because let's say A is small too, yeah. Okay. Yeah, right. But that even that is still NP hard, yeah. You see, right? If I give you a graph where the expansion is like let's say it is close to 1, then it needs to return this case where actually A is going to be empty and say that the whole graph actually has high conductance. And if the graph have expansion less than 1/1000, say, then 1 sec. I'm not sure how to argue about this formally right now, but I guess let's say that this is still NP hard, but it turns out that if we allow, instead of this, you allow this to be polylog, 1/polylog, then it turns out that you can actually solve it in polynomial time now, and actually in almost linear time. Yeah. And I think I'm gonna and do you see that? Suppose that you are given this subroutine, then you are done. The reason is that what you do is just, as long as the algorithm returns this case, then you keep using that cut, but it's not gonna happen more than log n times in the cut matching game. And otherwise, the algorithm will return this kind of cut, which means that you get some A and the rest B, where it's not like as good an expander as before, but still very good, still like a 1/polylog expander. And if you just say that in the last round, what we do, we just add a matching from A to B, then the whole graph will still have after adding this blue matching, the whole graph gonna have this to be 1/polylog, maybe over 4. You get this thing, you still get this kind of expansion, but maybe worse by 1/3 or something. Yeah. And so you still get an expander, right? So this subroutine is really enough. But how to really get this subroutine? Maybe I will try to outline things in the homework so that you can really see how to get it. Yeah. Okay. Right. Okay, so basically the way to get this is you can kind of keep finding sparse cut again and collect it. If keep finding sparse cut, if all of them together is balanced, then you get the first case. And if you keep trying to keep finding sparse cut, but everything that you have found so far is small, then it means that the rest is already an expander. That's the idea, but yeah, we can try to make it formal in the homework. Okay. So actually, I don't have anything much to say from now. May I ask you, like, how do you think of the class so far? Do you want some, what kind of topics that you would want to see in particular, or like how is the pace? I don't know. Yeah, I want to get some more feedback. Yeah. Yeah, it's gonna come like in 2 weeks or something. That's gonna be like, yeah, very cool thing in this class. Yeah. Right. Right. Yeah. So then that's it. Yeah.
So in that redefining of sparsest cut, what if the set we are accumulating is not becoming sparse at any time, and how do we guarantee that we definitely find a set that is sparse without checking all possibilities?
So you are asking about this how to get this subroutine from keep fighting sparse cut, or
Yeah, I mean, yeah, greedy sparse cut, how can we get this guarantee?
yeah. So let me just say again. So like so I'm like in like when we were talking about latent route and so on, right? At that time we said that we have an algorithm for approximating conductance up to log factor. Okay, so in particular what we have is this. Given a graph, input a graph, it either say that so we were talking about conductance, but it is going to be true for expansion too. This is going to be like maybe either return cut S where the expansion is less than this, which means that the expansion of the whole graph is less than 1 over 100. Or say that the expansion of the whole graph is already log n, right? So you can even like, if you can approximate it up to log n factor, you can solve this one. Okay, and now given this subroutine, well, if we want to solve this, then we just do greedy, right? If you find a sparse cut S, you find it, and find another sparse cut, and keep finding this. And if none of them, like if you cannot find anything more, but okay, once this union is big, it's like a 1 over 4 balance, then you get this case. And the reason is that the union of sparse cut is going to be sparse cut as we discussed in class, right? So, but if at some point you cannot find more, like if let's say that this is still small and you cannot find any more sparse cut, it means that this is your B side. And it's exactly like, here it says that this part, the B side here, is actually 1 over log expansion. So that's how you get this case.
So in the case where the size of the S that we are getting is very small. Let us say we are only getting 2 vertices or 3 vertices per iteration.
Yeah.
So then to get to n over 4, it may take n over 12 iterations, right?
Right. So this algorithm is just polytime algorithm. Yeah. So you said that you might need to collect so many cuts before, like you need to call like n times. Yeah. So the algorithm I described here, okay, it's not linear still, but it's polytime. Yeah. And once we have seen cut matching game and other stuff and how to use cut matching game, we actually gonna see how to solve this thing, the purple thing, in near linear time. Yeah, this is possible to do in near linear. Yeah, at least randomized near linear, but deterministic is almost linear, like with n to the little 1 factor. Yeah. Right. Okay. So yeah, besides expanded decomposition, is there something that you really want to see in class?
Are there any applications of using degree constraint to cut constraint? That there is a like
Yeah, one is gonna be in the homework. So basically, I'm gonna ask you that suppose that, but it's gonna be kind of not very cool application, but still some application. That is, if you have an expander and you wanna check, you wanna solve MaxFlow on expander, okay? But say you want to get like just constant approximation of MaxFlow. Like you ask, you have let's say like you have demand between like S and T, and you ask if you can flow like by value of K, or like if you say that like let's say you want just 10 approximation of MaxFlow, yeah, then you can do it in sublinear time, just checking the degree is enough, something like that. So I'm not sure what other application are there, but yeah, I think you can try to see. Okay, then that's it for today. Yeah. Right.
Currently working on improving like deterministic vertex connectivity.
Yeah, I kind of working on it. You are in